so slow, and they allow all kind of tools. And at the end, the students, they come out of this course without knowing even, they don't go even beyond DC. Exactly the same that the way they teach at community colleges. I'm teaching upper division courses and the students still suffer. They are not taking my classes. They're taking classes with all kind of available tools, recording and faculty. They're not even going beyond. All they do in class, doing 2 examples on the board and just focusing on 2 examples. And by the time the semester ends, they don't even cover AC. And then they think that, oh, great, it was a nice course, everything was available. No, that's not nice. There are some hardship associated to engineering courses. And then what I'm saying is recording, this is whiteboard, blackboard, doesn't matter. You're in class, listen to the lecture, take time and draw. Do you want me to go slow? How can I go slow? Even my writing is in my handout. That's why I'm providing you with handout. What part of this explanation is not in the handout? Except the schematic. Sometimes I draw the schematic. And for the schematic, I keep it here. Right now, it's a good 10 minutes that this schematic is on the board. And I'm just asking how many nodes, how many branches? Why this takes time and it's so difficult to draw this? And examples, I do many examples in class when I'm teaching face-to-face. I do many more examples in class than whiteboard and online.
No, that's not difficult. I was just asking.
Okay. Let me go. Can I go to the next page? Can I erase it?
Can I just ask a question on a branch? So I know that you guys mentioned that there was 5 branches. Is a branch in between 2 nodes, like 2 essential nodes or
branch
2 simple
is
nodes?
Element. Branch is anything but the line. Line is not a branch. Line is just the perfect wire or conductor. Branch is a device or element that you insert in. It can be one element, anything that you insert along the way, it's a branch. So you have 1, 2, 3, 4, 5, 6, 7. In this case, if I insert this one, I have 7 branches.
So for example, like resistor, capacitor.
Yes, these are all branches.
Load.
Yes, they form branches.
Okay.
That's a terminology they use. And notice that these terminology, they don't even explain or anything. I'm just trying to, they just take it for granted that people know that. Many of these topics, back to something that somebody else mentioned before, many of these, they don't even lecture on it. I'm telling you. They don't even lecture on it. They just, if you take circuit course, many schools, you know what they do? After the first lecture, they put circuit, they apply Ohm's law, Kirchhoff's law, and they solve the problem. Nothing. I go through preparation process because I think you should prepare. You should become familiar with terminology before you start. Branch is any element that you insert is called a branch, and any connecting point is a node. Okay, let me ask this question. And again, this picture is on the board for a good 5 minutes. I hope you can already, I don't know, Word or whatever. Okay, let me go to this circuit. Suppose there is element 1, 2, and 3, and I want to bypass. Bypass some elements. Suppose you want to bypass 1, 2, 3. This is the physical circuit. You're in the lab, this is a physical circuit. They give you breadboard. And you want to bypass. Okay. When you bypass, physical bypass is not possible. You cannot detach element. But in circuit analysis, you're allowed to bypass element in order to reduce your work. How do you bypass? You draw a line around it. You draw a line around it. and you pretend that 1, 2, 3 is inside this closed path. So this is a closed path. You draw this closed path and you enclose 1, 2, 3 inside closed path. Pretend that you don't see inside. Actually, this closed path in this case, because of number 4, it's extended. This is your closed path. And pretend that you don't see 1, 2, 3. Pretend that you don't see inside. Okay, from outside, this looks like, this closed path looks like a big node. It looks like a node because you don't see inside. So what you see from outside, you see that element 4, 5, and 6, they are connected, and maybe 7, whatever. They are connected to this big node. But this is your made-up node. It's a node by design. You decide. You want to bypass 1 or 2, you draw your closed path here. You want to bypass 4 and 5, you draw your closed path here. So you can draw closed path to enclose some elements in the circuit, and from outside, you pretend that you don't see the inside. That fictitious, made-up node is called a supernode. Why do we define supernode? Because eventually, later, it becomes important method in circuit analysis to use supernode. Any question?
Professor?
Yeah.
How would it look if you made 4 and 5 into a supernode? How you were saying? I just want to see an example.
4 and 5?
Because you said it can be our choice to make a supernode.
Yeah.
All right, for sure. Thank you.
If you want to make 4, 5, 7 as a supernode, yeah. You just draw the line to enclose the elements, and the line is connected to the elements, and you pretend that you don't see them. Whatever is enclosed in your supernode, it's something that you bypass.
So bypassing is kind of like making it
you don't have to write detail, for example, KCL. You will see later. You can, okay. Instead of like this is something, we do this kind of action in circuit modeling. Suppose you're outside a room and there are, I don't know, something going on inside the room. Maybe people are fighting, whatever. You don't know what's going on. You just pay attention to how many people are coming out or what is coming out. So basically, the detail in process, the detail information is inside. That's exactly what's happening. But you really don't care about the details. You just want to know what is coming out. I don't care how much current goes through 1, how much current is divided here, how much current goes through 2, how much current goes through 3. I just want to know what it's, for example, let's say, what's eventually the final current that's coming out of this combination. What is coming out of the combination? In that case, in order not to get distracted, you can pretend that you don't see them. You just hear something going on in the room. You just go and close the door and let anything happen. You're only concerned about when the door is open and something comes out. But you really don't know, and you don't want to know about the details. That's basically the concept behind supernode. Any question?
So it doesn't act as like a conductor or anything?
What do you mean by conductor? Everything is a conductor here. It's a node. It's a connecting point. Node is a connect. Everything here is a conductor. So current goes here. Rather than current goes here divided into I1, I2, or current goes here divided I3, I3, you just consider I1, I2, and I3. That's it. You don't look at the vision part inside.
So you don't look at the P equals IV or none of the stuff inside. You just bypass it.
Yeah, you just bypass it. So, and you don't need to bypass at all times. Notice that when you're in the problem solving process, you can bypass, simplify, reduce the number of equations, get your answer. Now, if you need to know what's going on, take that answer and go back and look at the details. Like, for example, again, you just use this silly example. You see, for example, 2-3 people are coming out. That's the most important thing, how many people are coming out. But then after you count the number of people coming out, then you may want to know what's happening inside. Then you can go inside. You can always go inside and look at all the details. Remember, I'm not detaching anything here. I'm just bypassing. So anytime you need more information, you always have your original circuit. I always mention that when you do circuit analysis, you don't delete your original circuit. You always keep your original circuit. And then you do whatever you do, like in terms of bypassing and everything is part of the process. Anything you want to know, you change your mind, you want to go back and look at the details, you can always go back and details. But the good thing here is the result that you get due to supernode is always applicable to the original circuit because of the circuit laws. You're not violating circuit laws. So anything you get by bypassing, if you want to go back and look at details, you can still use the result that you obtained through bypassing. Okay, let's go to the next topic. I go slow so you can draw. Okay. Concept of loop. Loop is a closed path. Okay, closed path. Passing through elements or through the air. For example, let's say this is element 1, 2, 3, 4, 5. If I start from here, pass through 1, 2, 3. So this is node A, node B. And then pay attention. And then from B back to A. This is a loop. Okay, passing through element 1, 2, reaching B, and from B jumping through the air back to A. It's a non-physical loop. Because part of the loop, you're not passing through the element. This is a loop. Physical loop. You must pass through elements. Elements should be along the way. Okay, I use blue color. This is a physical loop. This is a physical loop. This is a physical loop. So I have 3 physical loops here. This is a physical loop. This is a physical loop. And this outer loop, physical loop. Okay, you tell me, forget about this non-physical. Forget about non-physical. Let's just focus on physical. Let's say this is loop 1, loop 2, and the outer loop, loop 3. What's the main difference between 1 and 3 or 2 and 3? Main difference. Pay attention to loop 1 and loop 3.
The path.
Paths are different, but there is one thing obviously different between these two.
The elements going through the loop?
Elements are going through the loop, they're different. But regardless, let's put it this way, regardless of the number of elements, regardless of different elements along the way, in terms of drawing, like a shape drawing, there is one main difference. Regardless of the size. Okay, look at the loop
Is
one.
there one more circular and one's more like oval?
No, because oval circular, it just depends on my drawing style. I can make it circular. Okay, look at loop one or loop two. When you go around, do you find any circuit element inside?
Yeah.
For loop one and loop two, do you have any circuit element, leftover element inside?
No.
No.
Hmm.
No branch inside. Okay, look at the outer loop. So for loop 1 and 2, for loop 3, outer loop, it's a loop. It's the borderline, but we also have some circuit elements inside. So you have some branches inside. Any loop that has no branch inside is called simple loop or mesh. Any element that has branches inside is called combined loop. So we have two types of physical loops. We have a loop that has no circuit element inside. It's called mesh or simple loop. Or you have a loop that has some circuit elements inside. You call it combined loop. That's it. Any question?
You said simple loop or mesh loop?
Mesh.
Mesh? Okay, thank you.
In circuit analysis, instead of saying, anytime you hear the word mesh, mesh is a simple loop. And we do have very important analysis later, mesh analysis, that's associated to simple loop. Okay, yeah.
For component number 3,
yeah,
since it's a branch in between two nodes, can that also be a loop?
A loop is, physical loop is a closed path. This is a loop. This is a loop. This is a loop. And there is nothing else. I don't see anything, any other loop, any other physical loop. What, can you tell me can you tell me how it's?
If I just thought if voltage was known at both nodes, if component 3 would be able to be like a non-physical loop.
Okay, non-physical loop I'm echoing my voice. Non-physical loop means loop between 3 and where? Loop, give me the loop path. Let me use a different color. What path you're talking about? Loop is a path. Loop is a path. So what path you're talking about? Number 3 and where? Going where?
Literally just the line going from B to the bottom line. It's a loop over that single line.
Loop is a closed path.
Okay, okay. Thank you for defining that.
Yeah. Loop is a closed path. Yeah. I mean, two ends should come together. 2 points should come together at the end. It cannot be open end. So if the one end is hanging, it's not a loop. Any question? Okay. These are all preparations. And they don't cover preparation. They don't mention preparation. They just assume that you know what's the preparation. So we have node, loop. Okay, ground. Ground is important concept. It's fully covered in power. Ground is the common point. or reference. Okay. I bypass the concept of ground detail. I just mentioned something because ground is something that you need to understand circuit analysis before you even, we do have many, especially in power area, ground problems. There are some disturbances, some power shortage, some power cutoff, all due to grounding problem. Sometimes you have noise due to the grounding. So ground is a topic by itself. But at this point, I just want to show you the notation. Anytime you go to the lab and you connect, let's say we have a source, and then we have some elements, and then we have another maybe element here, and we have another source here maybe. Okay, maybe something like that, plus or minus, plus or minus. In circuit analysis, when you design, it depends on application. It depends on application. When you are doing practical circuits, especially when you're using voltage sources, it's required that you have a common ground. Like the ground of the sources should be connected. But in this case, we have element 1, 2, 3, 4. In circuit analysis, you don't have to worry about ground problems. But in many circuit problems, you need to have a reference. Voltage is always a relative measure. It's a relative measure. It's a relative reading. Voltage is potential difference. So for example, when I have 10 volts here, 10 volts of plus with respect to minus. If I have, for example, 2 volts here, with respect to 2 points. So in case of circuit analysis, sometimes you need to define a reference point. Reference point may not be the ground point, maybe your choice of a reference point or the common point. Reference point can be any point. You will see later. Usually we choose the bottom line that everything is connected as our reference. Or you choose a line that most number of elements connected as your reference. But if somebody wants to use this point as a reference, that's fine. If somebody uses this point as a reference, that's fine. So ground or reference, by the way, the notation for ground like a ground, like an actual ground, physical ground, is this notation. So if anytime you see this notation, this is ground. It's a ground, like a physical ground. But usually in circuit analysis, you may not see this symbol because for circuit calculation, for circuit analysis, for physical circuit, proper grounding is important. I want to mention this several times. If you're a technician, if you're an engineer, if you're a power engineer, the proper location for ground is important. However, that choice when it comes to circuit analysis is not important, fortunately. So that's why for this circuit, we don't even pay attention to what is the actual ground. We have to choose sometimes a common reference point. But that common reference point can be any point. It doesn't have to be the real ground. So ground problem is something that if you're a student and if you continue in power, when it comes to, would you please, if you're not listening, that's fine, but mute your mic.
Sorry, that was me.
So when it comes to the ground, again, in a physical term, it's important, but fortunately in circuit analysis, it's not important. Any question about that? Again, this is all part of the preparation.
Are you going to go into more in depth later on?
No, not this course. Ground is something that they cover in power. In regular circuit, in small size circuit, in small signal circuit, first of all, this is analysis, circuit analysis. So we don't pay that much attention to technical consideration, technical wiring. But when it comes to actual power, like especially in power area, high voltage area, then you have to pay a bit. And electronics, also in electronics, when you take electronics course, we do talk a little bit about the common point or common ground, especially. And when I cover operational amplifier, I do cover op-amp. That's another thing that if you take it that, I don't know, many professors, they bypass. I don't bypass. I don't bypass operational amplifier. I do cover op-amp here because that's something that you're using in everything. When it comes to op-amp, I explain a little bit, but other than that, no. I mean, because grounding doesn't have any effect on your analysis parts. But when it comes to the technical connection, sometimes proper grounding, like if you're in the lab, and also if you take a circuit lab, maybe if you're an MES student, you don't need it, but electrical engineering students, when they take circuit lab, I think the circuit TA, they do talk about grounding and proper grounding a bit more. Okay.
So the reference line, we can think of it as like the parallel, like when it's connected in parallel.
No, has nothing to do with parallel, series, nothing. Reference point, you can choose any point, but usually when they give you circuit, you automatically choose, if you open the book, always you see a circuit with a bunch of elements and maybe a long line at the bottom of the circuit. You always choose that one as your reference, usually. But you can choose any point as your reference. Usually you choose a point or a line that has the most number of elements connected to. But again, it's something that it's 100% optional. That's a good thing about circuit. Pretty much anything is optional at the beginning before you start. Okay, the other thing is a connection format. I have already covered this. We have series, we have parallel. Series, back to back. They all carry the same current in any direction. Parallel, connecting between two same line. This is parallel to level and elements in between. They all have the same voltage. Different current, same voltage. Let me ask right away. This is my history in this course, teaching this course. There are some, I'm not saying all, some students, even up to senior level, they are still confused about parallel series. Now I always ask my class, why? What is so difficult? At this point, anything you say is perfectly valid because you're starting. Not when students, they're at the senior level about to graduate and they still go for interview and they still get confused about parallel, and the interviewer always say, what school did you go? I mean, you're still confused about parallel series. You tell me, you guys tell me, what is so difficult to see? Because this is visual concept. What is so difficult? What part? To see, series or parallel?
I mean, in identifying them, I think it's pretty easy.
Yeah, because it's visual. So let me try. I'm going to start with, sorry, I don't want, but I really want to make sure that people have a good understanding of this concept. Okay, I'm going to put 1, 2, 3, 4, 5, 6, and 7. Okay? 1, 2, 3, 4, 5, 6, 7. So I'm going to start taking go now and participate, because this one you have to know. Before I start anything, I haven't even started my laws, but I want to make sure that you have a good understanding. Aguilar.
Here.
Okay. In terms of box numbers, which boxes are connected in series? And don't worry, this is the time that even if your answer is wrong, you should not feel embarrassed or anything, because it's the beginning. But if I ask this question at the end of the semester, then it's not acceptable. But now it's okay. because I'm trying to correct your confusion. Which elements are series?
1, 2, 3, 6, 7.
Okay, no. Give me as a group. Give me as a group. So 1, 2, 3 are series with respect to each other, right?
Yes.
6 and 7, series with respect to each other. Okay, let me go to Alejandro. Is this group in series with this group?
No.
Why is that? Because we are branching off in the middle. Series means simple node in between. Okay, so that's why the when previous students said 1, 2, 3, 6, 7, I said we have to separate them. Yes, 1, 2, 3, they are connected in series.
Professor?
6 and 7, they are connected in series. But notice that in between we have a branch. A branch is opening. This node is not a simple node. This node is essential node. So the current is branching off. So 1, 2, 3, they are in series with each other. 6 and 7, series in each other. But 1, 2, 3, they are not in series with 6 and 7. Is that okay? Okay. Amador?
Yes.
Give me current, assign current. Don't worry about direction, any direction. Just give me current I1, I2, I3, whatever. Assign a current to element 1. Up or down doesn't matter. Let's say up. Let's say I'm going to start. Let's say this is I1. What's the current passing through 2?
The 1.
I1. What's the current passing through 3?
I1.
Okay, what's the current passing through 6? Any direction, doesn't matter.
I1, I think.
Is this the same? So what happens to this branch?
They're
Okay,
separated. It's not the same.
I1 arriving at this node. I1 arriving at this node. Arellano, are you here?
Here.
Okay, I1 arriving at this node, what happens to I1? Think about a current, like a water flow. The water is arriving at this node. What happens to I1?
Is it gonna like separate to 2 different?
Yeah, separate. A branch goes here. Portion of it goes here. Portion of it goes here. Portion of it goes here. Right? Okay, Argandona.
I'm here.
If this is I6, then what current goes through 7?
Would it still be I6?
Yes. So I'm going to call the whole thing I1. This whole thing I6 because they are in series. In the middle, they are branching off. 1, 2, 3 in series, 6 and 7 in series. But they branch off. Again, don't worry about direction. I'm just using direction. You can choose any direction. Eventually, KCL at the end justifies the direction. And then we have 2 branches, so they are separated. Any question? Okay. Asensio?
I'm here.
Yeah. Parallel.
It's going to be 4 and 5.
Yes. Bernal.
I'm here.
That's it. Do you see any other parallel? I mean, single elements, not combination, single.
For single, there's no others that are single and parallel.
I mean, you don't, 4 and 5 are the only one you see, right? Okay,
yes.
Good. Abdul Castaneda. Are you here?
Yes.
Okay, let me start assigning voltages. Again, don't worry about polarity or anything. I'm going to start here. Let's call this one plus or minus V1. Don't worry about passive sign, nothing. Just put plus minus V. Okay, this is V1. What about this one? Is this V1?
So in series, the voltage is added, and in parallel, they're
No, don't add. This is at this point just
4
assigning.
and 5, they're constant.
So I'm just going to call name. This is just name assignment. I'm going to call this one V1. My question is, the voltage across V2, should I call it V1 again?
No,
Okay, V2. Should I call this one V1 again?
no,
V3. 4 and 5. I'm going to call this one plus or minus. Let's go to Castro. Across 4, I'm going to call it V4. What voltage should I put across V5? Castro, V1? Are you
Yes.
here? Yeah. What voltage should I assign to number 5?
Would it be tempted to say V4?
Yes. V6,
V5?
6 is in, different. You meant different, right?
Yeah.
And the different, and then I'm going to call it this 3-7. So what happens when you have parallel elements? As long as they are in parallel, they all have the same voltages, but they have different currents. If they are in series, they all have same currents, but different voltages. That's the conclusion. I think so far, based on you guys answering the question, I think you all have good understanding, hopefully. Any question?
So in series, same voltage,
Same current,
same current, different
voltages, yeah.
And then in parallel,
Same voltages, different currents.
okay, thank you.
I did this before, but let me do it again. Suppose you have a bunch of elements in series. So they carry the same current. Again, any direction. At this point, don't worry about the direction. I1, it's a loop current. I or I1, whatever. Dorian, Claire.
Yes.
I open the terminal here. I cut the terminal. Take a scissor and open. What happens to the current?
It stops where you cut it.
Current goes to 0. What about voltages? Do they go to 0?
I would say no.
No, voltage doesn't go. Voltage is like, I mentioned before, always use this vision. Imagine this, that some people are in second floor, some people are in the first floor. And you have elevator or, I don't know, stairs. As long as you provide the stairs or elevator, you have a flow. They go back and forth. But now you have a bunch of people on the second floor, you have a bunch of people on the first floor. And then you cut the connecting pathway, you stop the elevator or you remove the stairs. You still have separation. You still have people. That's charge accumulation. You still have positive, negative potential difference, but there is no flow. So if the current goes to 0, doesn't mean that the voltage goes to 0, unless if you have a passive element that we discuss later. But you should say not necessarily. So maybe there is a voltage. This is between point A, point B. Even though there is no current, through open circuit. This is called open circuit. Open circuit. I goes to 0, but if you have voltage, may not be 0. Of course, it depends on the rest of the circuit, may not be 0. You still have a potential difference. Okay, Contreras.
I'm here.
Suppose you have a bunch of elements I did this before, but I want to emphasize. All in parallel. Then between this node and this node, at any location, you take a wire and connect it. What happens?
Should it just be the same as the other nodes?
No, you just take a wire and short. This is called short circuit.
Oh, wouldn't the nodes beyond that wire be like?
But what happens to the potential difference? Like this, before I disconnect, I had some voltage values, let's say plus or minus V. And because it's parallel, they're all the same. As soon as I short, what happens to V? There is no potential difference. Shorting means you have second floor and the first floor, right? Shorting means you bring second floor, you push it down, you make it at the same level as the first floor. Short circuit means that you remove that bump, the difference. So the potential difference of a short circuit is zero. Because it's parallel, the whole voltage across the whole thing goes to zero. All the current coming, it goes through the short circuit. So shorting, anytime you connect a line across a short circuit, you short anything, the potential difference goes to zero.
Professor?
Yes.
Does that mean that it takes away the power from all elements in the circuit?
Yes. It's not wise to short a source. I'll talk about that technical problem later when I cover Ohm's law.
Because it would burn out?
Yes. You burn out the power supply, and you see why, because of the Ohm's law. So you don't short the source, but you can short passive elements.
So on resistance, when there's no connection.
When you short, there's no power. Nothing goes into the resistor.
No, on the open one. So on the open circuit, it's called open line, right? When there's resistance.
Open line. Even for passive element, if the current goes, if I have a resistor here, covered that. If you have a resistor here, passive element, because if the current goes to zero, there is no power. If the voltage goes to zero, there is no power. So even for the resistor, even if you open it, the voltage goes to zero.
Can't the current arc the open line?
But for that one, sorry?
Can't the current it arc over the open line and still go through it?
No, those are you're talking about the Tesla experience that happens only in power system, that you must have a huge voltage current in order to air particles to create that somehow light. That's called the Tesla experiment. No. I'm talking about Tesla. I think you case that we don't have an area in between some kind of we're not talking about charge transfer through the air, the photon particles that may happen here. Because it's easily, notice that air is insulated. Insulated means you have a balance and you have a conjunction band. You have a very large energy gap. The reason that insulator doesn't allow current to go because that current doesn't have enough strength to move electron conjunction band. If you can move electron conjunction band in any situation, you have some flow. Air is insulator. Regular electric doesn't have enough electric signal doesn't have enough strength to move electron in the air energy gap. But if you have a large energy, that large power is capable to move large force. This is the thing that you have. This is very high hill. You don't have enough energy to climb that hill. But if you have a huge force behind you to push you up, then you can overcome that area. So these are the cases that you have some special cases. We don't have rubber. Those are just 100% special cases.
So we do that area as a measure of resistance.
Yeah, almost like meteorite resistance. Yeah. Okay. All easy. Let me continue my thing because okay. So let's say I have a source here. It's just a simple question. This is element A, B, and C. It just follow because Delhi. What is the frequency? If they give you a second. Delhi. Are you here, Delhi? Delhi. I usually repeat 4 times. Delhi. Okay. Estrada. Yeah. Okay. What is IC?
IC is the same as ABB was 2A.
2A.
Yeah.
What about the problem? Gives you and they ask you what is IC? Then what is your answer?
The same thing, I think.
What's the direction of my current? Going down. But the problem can ask you in any direction. So your answer in this case.
Plus or minus.
Minus. Okay. Garcia. Jose Garcia Sandoval. Okay.
Yeah, I'm here.
Okay, let's say we have this case. What's the voltage across A?
The same voltage, so it will be 6 volts.
Yeah, anyone with voltage source in Cali, with anything, the voltage for all elements given. I've seen this in the voltage calculation. It's given. What about if the problem can ask you any question? What about the problem is asking you this? Find the answer.
That will be the same 6 volts.
It has a question in problem has different polarity. Opposite polarity.
Negative, yeah.
Okay. Good. Jose Eduardo Garcia. Are you here?
Yes.
Okay. Let's assume that we have a node. And we have a bunch of branches. Sorry. And the current is given I1, I2, I3, I4. They all come to the node. When you think about energy conservation law, this is not an energy conservation law. But if I ask you to formulate the current situation, how only fractures come to the node, what do you think? It's the proper formulation in this case. Find the relationship I5. What do you say?
I would say I2 plus I4 equals I3 plus I1.
Yeah. This is called current assessment. The summation of the currents entering equal to the summation of both current leaving. Okay. Good. So you're giving lectures in the big lecture. This is called here. For any node, simple node, essential node, super node, just pay attention to the branches connected to the node. Summation of all the current branch equals the summation of connectivity. Important warning. Do not have the numbers. Systems that get distracted by minus plus. So for example, in this case, I give you I2 to minus 2 amp, I1 equal to plus 4 amp, I4 equal to minus 6 amp, and the output point I3. Don't get distracted about minus sign. Just pay attention to the direction. You still say I2 plus I4 equal to I3 plus I1. No, when you plug in values, it's minus 2 plus minus 4 equal to I1 plus 4 plus I3. From this equation, I3. I know that the students, they get distracted. They say, okay, and anything, minus, so it's going to make it's actually leaving. Make up your mind. Do not touch the minus sign. Do not change anything. Just pay attention to the direction, current entry equal to the current lead. You will apply when you branch because if you have simple nodes, it's the same part. Okay, Sebastian Gonzalez. Let me ask you this question here. Actually, let me do the following so we go beyond my minute and then make it clear so things come out. Haru, Manuel Haru. Hermosillo.
Here.
Yanes. Here. Ailey.
Here.
Leon.
Here.
Macias.
Here.
Melendez.
Here.
And Mendiola.
Here.
Monge.
Here.
Moreno.
Here.
Nunes. Pedro.
Here.
Sarabi. Nunes. Moreno.
Here.
Portillo.
Here.
Rivas.
Here.
Robles.
Here.
Rocha.
Here.
Janet Rodriguez. Janet Rodriguez. Marlene Rodriguez.
Here.
Roas.
Here.
Rosales.
Yes.
Sabino. Samai.
Here.
Siodia. Edith Siodia. Raymond Tran.
Here.
Yani Valencia.
Here.
Lasquez.
Here.
Belamel.
Here.
Rivaldo.
Here.
Zaragoza.
Here.
Okay. I just maybe spend 1 more minute to say something, and then I'll maybe a few more minutes to say something, and then I'll continue. Yeah, sure. What's your last name? Delhi? Okay, yeah. Okay. Anybody else? Okay, so let me pay attention to the formula here. If you read the book, usually in the book they don't say entering, leaving. They just say summation of algebraic sum of the current equal to 0. What's the difference between this statement and this one? This one is easier. It's the same thing. It's the same formula. Summation, current entering equal to the current leaving. But in the book, they usually put one summation equal to 0. They're the same. In what way are they the same? In what way? What do you think? What's the difference between the way that I'm explaining and the way that the book is defining KCL? This is KCL. Anybody has any opinion?
Seems like the book way is saying summation of all current, and you're kind of breaking it down from the entering and leaving.
Yeah. The way that book says, okay, make up your mind. If it's entering, regardless of the value, just a notation, regardless of the value. If it's entering, put plus in front. If it's leaving, put minus in front. This is option 1. Or, if that's the case, this is the way that book defines. Okay, what is entering? Plus I2. What else is entering? Plus I4, regardless of the value. And then minus I1 minus I3 equal to 0. This is called algebraic sum. Notice that this is equation. You can terms from left to right or right to left. Or the book says, if it's entering, these are all the options you have. Put minus in front. If it's leaving, put plus in front. Okay, so what happens in this case? What is entering? Minus in front. Minus I2, minus I4, plus I1, plus I3 equal to 0. It's the same. So summation of currents entering, say anything entering, I put plus in front. Anything leaving, I put minus in front. Remember, please remember this. And if you're still confused about that, let me know. When I say entering, put plus, leaving, put minus, this is outside plus minus. The value itself can be either positive or negative. That has nothing to do with the value. But I personally prefer my way of saying the summation of all the currents entering, put entering on one side equal to the leaving on the other side. I think it's more clear. That's it. That's KCL. I have nothing else to say about KCL. There is no special case. There is no tricky case. You just look at the node. Node can be just a simple node. It can be a super node. For example, you may bypass circuit. Let me just show you one case. You don't even have to, we do it later. Let's say we have, remember we had example before? We had some elements in the middle. Maybe some elements in the middle. You can bypass the whole thing here. Let's say this is your super node. Let's say I1, I2, I3, I4, for example. You don't have to look at the details. Somebody mentioned what's the point of supernode. You can apply KCL at this node. You can apply KCL at this node. But here you can also bypass some elements and just say I1 plus I3 equal to I2 plus I4, for example. Okay. And one last thing, absolutely last thing. If you look at this circuit, you apply KCL to essential nodes. Because when you have a simple node, when you have series element, they have only one current. Back to this example. How many essential nodes we have? We have 1, we have 2, this is essential node. We have 3, we have 1, this is simple node, this is series. We have 2 and we have 3. In order to solve problem, if you have n essential nodes, you use n minus 1 for KCL. The nth node is repeated information. For example, in this case, If I write KCL equation for node 1, if I write KCL equation for node 2, that's enough. I don't need to write KCL equation of node 3. Because essentially, if you write KCL for node 3, it's going to be a summation of these two. It's a repeated information. It's not new information. So if your circuit has 100 essential nodes, you just need to write 99, for example, KCL equations. That's another thing about KCL. I finished KCL today, and I'll continue with KVL, which is a bit more challenging, and Ohm's law. Meanwhile, today is the due date for the homework. Please send your homework until midnight. And then after collecting homework, I'll send you solution. I'll check homework. You have to show some meaningful work, like it doesn't have to be 100% correct. If you just write problem and maybe few answers or maybe few, I don't know, maybe numbers or something, I'm not going to accept it. Remember, homework doesn't give you any added point because it's part of your responsibility to do the course. And also their solution sets are available. So I don't feel comfortable to give a point because some students don't have access to the solution. So that's why I just check your work and put a check mark. However, if you don't submit homework, you're not following the guideline, there is a 2-point deduction. And 2-point deduction after I assign 10 homework by the end, like 20-point deduction is major. It's very simple, easy guideline to follow. Just show some work and send it to me. And there is no rule or guideline for the format. The way that you solve it, you can do it handwritten or use tablet. But please convert to one PDF. Take a picture, convert it to one PDF. And make sure that in your subject box, when you send it, you mention EE or just 20, 40, homework 1, because I have a different folders. And if your homework is not acceptable or if you don't submit, I usually send you a notification. I don't know, some students, they don't like notification, but that's my way of keeping you in touch with the course. So if you don't send homework, or if your homework is not acceptable, I send you a no homework number 1 notification, just to let you know that you didn't submit or your homework number 1 wasn't acceptable. If you have any question, you can stay longer. Otherwise, have a good day.
Yeah, Professor, on I1 plus I3 equals I2 plus I4, can you explain that one more time? Because I'm trying to see how you did it. Because
I use a supernode in this case. I use supernode for this example. I didn't do node by. So the supernode is your drawing fictitious node. Okay, so I draw this big node. The point here is pretend you don't see inside. KCL allows you to apply, Kirchhoff's current law allows you to apply Kirchhoff's law to all the external lines that they connected to the supernode. So I have 1, 2, 3, 4 branches connected to this big node. I have the option of writing KCL for node 1, KCL for node 2, then I have to assign current for these 2 boxes and write KCL for node 1 and KCL for node 2. However, I can also bypass some nodes and write KCL to the big node that I'm drawing line around it, around some elements. So I have 1, 2, 3, 4 branches, I1, I3 entering, I2 and I4 leaving. So KCL equal to the summation of the current equal to the summation of the current leaving, regardless of your node being essential node or supernode. So the point of this example was sometimes rather than writing detailed KCL for each node, you may, depending on the problem, if it's appropriate, you can bypass a bunch of them and write KCL for the outer lines connected to that node.
Okay, but I'm still not getting like the order. Why'd you put them in that order?
How many currents entering?
We have 4.
The arrows help. Yeah.
Okay,
the arrows, I1 and I.
Which current?
Oh,
No,
the arrows. Okay.
Okay,
Yeah.
the arrows, yeah. The arrows shows the direction. I1 is entering, I3 is entering. Which currents are leaving? The arrows show I2 leaving, I4 leaving. Summation of the current entering equal to the summation of the currents leaving.
Okay, I got it now. I was thinking it was like a parallel or
No,
series thing.
no. When you apply, don't just always in circuit analysis. I always say that think simple, do not confuse, because especially when you have numbers like -2, -4, don't even look at the numbers. Just look at the arrows like current entering, current leaving. Write your equation, then you plug in values. Okay, if you have any more questions, please ask. Otherwise, have a good day.
Professor, I had a quick question in
Yeah.
regards to the homework before I submit it. If I have an element that doesn't have an assigned polarity, but I know that the current is leading the positive side of, like, per se, a battery, is it safe to say that it's going to be entering the positive side of the polarity? Can I just make up a polarity, or or is there like a certain...
If the polarity is not given and the direction not given, you can assign polarity and direction on your own, regardless.
What if I'm given direction, like my current is given, but I
Okay,
have no...
if the current, you still have option of using passive sign or non-passive sign, because your minus sign, the minus sign at the end justifies your direction.
Okay.
Or your polarity.
So then if I do passive, non-passive, it doesn't matter because it'll be the same answer no matter what?
Yeah.
Okay. Okay,
No
thank you very much for the clarification. All right, Professor, thank you.
Sure, no problem. Thanks.